Good morning, all of you. Welcome to Sri Jayendra Rank Zone. So we are in lecture 7 of group 17, group 14 elements. Now we are going to start about silicon. We have done already compounds of carbon. Now we are going to discuss compounds of silicon in this lecture. This is very, very important because from this chapter you will get questions based on silicon only. So please listen carefully. So let us start now. So compounds of silicon. So this is the second element in the group 14 elements. So the important compounds of silicon are silicon dioxide, silicones, and silicates. So all these three are very important because silicon dioxide is nothing but sand. It's also called as sand. Silicon dioxide, it is acidic in nature. Silicon dioxide is acidic in nature. And silicones and silicates. So all these three are very important. Definitely you are going to get one question for entrance exam from these compounds only. So please listen all the topics carefully. Next continuation. So this is silicon dioxide first. This is commonly occurred in combined form of silicon. Combined form of silicon. It is available in several crystallographic forms like quartz. Quartz is nothing but say glass. It's an amorphous form of glass, cristobalite, and tridymite. Tridymite. These forms are interconvertible at suitable temperatures. Silicon dioxide is a three-dimensional network solid, and each silicon atom is covalently bonded to four oxygen atoms. So each silicon atom is covalently bonded to four oxygen atoms tetrahedrally. So on the whole, it will form silicon dioxide. Each oxygen is bonded with two silicon atoms, and each silicon with oxygen making it again covalent network solid. So this is very, very important. This is covalent network solid, silicon dioxide. It forms tetrahedral structure in which each silicon atom is covalently bonded to four oxygen atoms. So based on the structure of the give statement-based question. So silicon dioxide is a three-dimensional network solid, and each silicon atom is covalently bonded to four oxygen atoms tetrahedrally. sp3 hybridization. So each oxygen atom is bonded with two silicon atoms and each silicon with one oxygen, making it again covalent network solid. So this is a structure of silicon dioxide. We have three-dimensional silicon dioxide structure. You can see here. This is the exact structure of three-dimensional structure of silicon dioxide. It's very, very important. So each silicon is bonded with two oxygen atoms. You can see here. Each silicon is bonded to one oxygen atom, two oxygen atom, three oxygen atom, and four oxygen atoms. So each silicon is bonded to four oxygen atoms. You can see 1, 2, 3, 1, 2, 3, and 4 here. So this is nothing but it's a continuous process. So this is called, and each oxygen atom is bonded with two silicon atoms. Each oxygen atom is bonded with first silicon atom, second silicon atom. The entire ring will be like this. So each oxygen atom, each oxygen atom is bonded with two silicon atoms, and each silicon is bonded with four oxygen atoms. Four oxygen atoms. So this is called silicon dioxide. Three-dimensional structure of silicon dioxide. Each oxygen atom is bonded with two silicon atoms, and each silicon atom is bonded with four oxygen atoms. So this is called silicon dioxide. Very, very important. Please make a note of it. Next continuation. Silicon dioxide. Silica or silicon dioxide is inert for halogens, means it is not reactive with respect to halogens, dihydrogen, acids, etc. But it reacts with hydrogen acid, that is hydrogen fluoride and sodium hydroxide. Silicon dioxide, when combined with sodium hydroxide, being acidic, it is acidic and it is basic. So it forms sodium silicate. This is called sodium silicate. Sodium silicate. Sodium silicate. And this is used, this silicon, for removing basic fluxes, for removing basic impurities in metallurgy. Silicon dioxide is used. Basic impurities or basic flux. You can call it as basic flux. Flux in metallurgy. We'll use silicon dioxide in metallurgy. silicon dioxide is used because it is acidic flux. Metallurgy, silicon dioxide is used. What is used? Silicon dioxide is used because it is acidic flux. So silicon dioxide combines sodium hydroxide and forms sodium silicate, which is removed as slag. It is called as slag. So flux plus impurities, it is called slag. Sorry, gangue plus flux is equal to slag. So this is called sodium silicate. Silicon dioxide on reaction with hydrogen fluid forms silicon tetrafluoride and water. Silica gel is used as a drying agent and support in chromatography. Silica gel is used as a drying agent in supporting chromatography. Chromatography is based on adsorption. Chromatography is based on adsorption. Quartz is piezoelectric and is used to develop clocks. Quartz is piezoelectric and is used to develop clocks. So silica gel is used as a drying agent in supporting chromatography. That is the process called adsorption. In chromatography, adsorption takes place. This adsorption topic you will be knowing in 12th class in surface chemistry. So this is called silicon dioxide. It is inert for most of the compounds, that is halogens, dihydrogen, acids, etc. And it reacts with only hydrogen fluoride and sodium hydroxide. When it combines sodium hydroxide, it forms sodium silicate. And with hydrogen fluoride, it forms silicon tetrafluoride. Silicon tetrafluoride. Next continuation. Silicones. Next we have, this is about silicon dioxide. More about silicon dioxide also you can write. I'll add some more points to silicon dioxide. Let us see now. So before going to silicon dioxide, so we'll see silicon dioxide, that is sand. It is also called as sand. It is mainly commonly known as silica. 95% of the Earth's crust is made up of silica. So you can see here some important points of silicon dioxide. Still I'm writing about silicon dioxide only. 95% of Earth's crust, Earth's crust is made up of silica, that is sand. Since you already know, silica occurs in many crystallographic forms such as quartz, cristobalite, and diatomite. These are interconvertible at suitable temperatures. And more important point is silicon dioxide also combines with calcium hydroxide. And forms calcium silicate. Calcium silicate, which is removed as slag plus water in the extraction of metals from metallurgy. And silica is insoluble in water but dissolves in water to a small extent when heated under pressure above 385 kelvins. So silica is insoluble in water. Silica is insoluble in water. This already we know. Silica is insoluble in water. Silicon tetrafluoride readily combines with again hydrogen fluoride and forms H2SiF6. H2SiF6. It can expand, it can due to the formation of H2SiF6. Silicon dioxide present in the glass dissolves. Therefore, HF cannot be stored in glass bottles. Due to this reason, HF cannot be stored in glass bottles. HF cannot be stored in glass bottles. So, next, silicon dioxide on reaction with carbon. Silicon dioxide on reaction with carbon forms silicon carbide. What is this called? Silicon carbide plus carbon monoxide. Silicon carbide is also called as carborundum. It is called carborundum or silicon carbide. Carborundum or silicon carbide. This is called silicon carbide or carborundum. So these are the additional points based on silicon. And all SiO bonds are very strong in silica, relatively inert and has very high melting point. And silicon tetrafluoride thus formed dissolves in HF. This is also we discussed. So these are the important points based upon silica. So the silicon dioxide is majorly used as acidic flux in metallurgy. It is used as acidic flux in metallurgy. Silicon dioxide is used as acidic flux in metallurgy because of its acidic nature. So these are the major points about silicon dioxide. Next, we are going to discuss about silicon. So please make a note in your classwork all these points because these are not present in the form of PPTs. I have written in the form of uh, with the pen. So that's why you please make a note of all these things. Next, we are going to discuss silicones. These are argon silicon polymers. These are argon silicon polymers that contain R2SiO repeating unit. Very, very important. They'll ask this question based on structure. So structure-based questions are important. So these are argon silicon polymers that contain polymers means so many molecules is joined together. So that is R2, that is ethyl or methyl. R is called alkyl group. Here R is called what? Alkyl group. R aryl substituted. As I told you, R is alkyl or aryl substituted chlorosilanes and subsequent polymerization. These are found by the hydrolysis of alkyl aryl means C6H5. Aryl means what? C6H5 substituted chlorosilanes and subsequent polymerization means first they are prepared by the means of hydrolysis of chlorosilanes, and after that they undergo polymerization. When methyl chloride is reacts with silicon in the presence of copper as a catalyst at a temperature above 500 kelvins, various type of methyl substituted chlorosilanes are formula MECA-SiCl3, Me2-SiCl2, Me3-SiCl with small amount of Me4Si are formed. So these are nothing but substitution reactions. What are these called? Substitution reactions. In place of chlorine, in place of methyl group, substitution reactions. Chlorine methyl is substituted. Substitution reactions where alkyl group is substituted in the place of chlorine. What is substituted? Alkyl group. Alkyl group is substituted. Alkyl group is substituted in the place of chlorine. Substituted in the place of chlorine. So what is this? When methyl chloride, that is CH3Cl, reacts with silicon in the presence of copper as a catalyst at a temperature of 573 kelvins, various types of methyl substituted chlorosilanes are formula MeSiCl3, Me2SiCl2. So in each case, one Cl3 is going off. Me3SiCl with small amount of Me4. Finally, all the chlorines are removed and replaced with alkyl group, that is methyl group. So are formed. So these are nothing but substitution reactions, and this is the preparation of silanes or silicones. Next continuation. Hydrolysis of dimethyl chlorosilane, CH3 taken twice, SaCl2, followed by condensation polymerization yields straight chain polymers. Yields what? They yield straight chain polymers. You can see here 2 moles of methyl chloride combined with silicon in the presence of copper powder at a temperature of 570 kelvins. It forms dimethyl silicon dichloride, and which on hydrolysis in the presence and forms CH3 taken twice, SiOH taken twice. And these are nothing but straight chain silicones. Straight chain silicones. These are nothing but what? Straight chain silicones where you have CH3, SiO, CH3. That is dimethyl dichlorosilicane. So in the presence of chlorine will be removed off. So this is called dimethyl dichlorosilicane silicone. This is called what? Silicone. Very, very important. This is called silicone. You can see first methyl group, second methyl group. So SiO, R2, R2SiO, R2SiO, where O is linked with another silicon and R is not linked with any other thing. So R2SiO, O, R2SiO, you can say simply, this is called silicone. This is called what? Silicone. Very, very important structure. Definitely they'll ask structure-based question based on this. So you need to be thorough with the structure. So it is nothing but it comprises of so many units of R2SiO, R2SiO, so many units of R2SiO that is undergoing polymerization. What is polymerization? What is polymerization? Here, the property of so many molecules, small molecules combined to form giant molecules. Small molecules are combined to form giant molecule, are combined to form giant molecule. Giant molecule means big molecule. So giant molecule, these are called, small molecules combine to form giant molecule. So these are called polymers, and the property is called as polymerization. So it is nothing but straight chain polymers. Straight chain polymers. These are called silicones. Please make a note. Very, very important. Definitely they are going to ask questions based on silicones. Next continuation. The chain length of the polymer can be controlled by adding, the chain length of the polymer can be controlled by adding trimethyl silicon chloride. Trimethyl means three methyl groups, which blocks the ends as shown below. They will block the end as shown below. You can see here. So this on reaction with polymerization, it will block the end. So this is the end of this compound. So it will block the end like this. So you can see here. So this is called chain length of the polymer can be controlled by adding trimethyl silicon chloride. By adding trimethyl silicon chloride, the polymerization, that polymer is being blocked. So this is called silicones. Next continuation. Next, we have silicates. What are silicates? In silicates, we have many types of silicates. A large percentage of Earth's crust consisting of silicate minerals are aluminosilicate clays. So, majorly, Earth's crust consisting of these silicate minerals only. The silicate minerals are majorly feldspar, mica, zeolites, asbestos. These zeolites are nothing but these are called as shape selective catalysts. What are zeolites? They are called as shape selective catalysts. Shape selective catalysts are called geolites. These are used as catalysts. A geolite named Jdesm-5. Geolite named what? It is called Jdesm-5, which is used to convert. It is used to convert petrol. It is used to convert, sorry, alcohol to gasoline. It is used to convert. Yes, here it is used to convert alcohol to gasoline. This point is very, very important. So many times they asked in the objective alcohol into gasoline, petrol. ZSM5 is a name of geolite. The structural units of silicates is SiO4 4 minus, in which silicon atom is bonded to four oxygen atoms in tetrahedral fashion. In silicate, either the discrete unit is present or the number of such units linked together, they form chain, ring, sheet, or three-dimensional structures. So in silicate, we have they either the discrete unit is present or number of such units linked together, they form chain, ring, sheet silicates or three-dimensional structures. So that's why we have different types of crystals, different types of silicates we have. So some of the important types of silicates we are going to discuss now. So this is very, very important. Please make a note. So the silicates are nothing but they are minerals of feldspar, mica, zeolites, asbestos. Next continuation. So this is called silicon tetrahedral structure of Si4O minus. Each silicon is linked with four oxygen atoms in tetrahedral fashion. Each silicon is linked with four oxygen atoms in tetrahedral fashion. Two important man-made silicates are glass and cement. The two important man-made silicates are glass and cement, which are very widely used since already we know glass is useful for many purposes like construction of cement is for construction and glass for window panes, etc. Windows, etc. So that's why the silicates are very, very important. It's of vital use. SiO4 4 minus, it is undergoing tetrahedral shape. So our automatical hybridization is also sp3 tetrahedral shape, and our hybridization is sp3 hybridization. It undergoes what hybridization? sp3 hybridization because of its tetrahedral shape. sp3 hybridization. So please make a note of all these points. Next continuation. Definitely, they are going to ask about structure. Next, geolites. These are microporous alumina silicate minerals. These are microporous alumina silicate minerals, also called as shape selective catalysts. Shape selective catalysts. So, geolites are shape selective catalysts. If aluminum atoms replace few silicon atoms in three-dimensional network of silicon dioxide, overall structure known as alumina silicates acquires a negative charge. Zeolites have a porous structure that can accommodate a wide variety of cations, such as sodium ion, potassium, calcium, magnesium, and others. These positive ions are rather loosely held and can readily be exchanged for others in a contact solution. So, this zeolites will be in exchange with alumina. Zeolites will be exchanged with alumina. Very, very important zeolites. Definitely, you're going to get question. Zeolites are used as a catalyst, as I told you, as a catalyst in petrochemical industries for cracking of hydrocarbons and isomerization. To convert alcohol into gasoline, we'll use a zeolite named ZSM5 as ion exchanges in softening of hard water and as a molecular sieves for the preparation of component mixture. For the preparation of component mixtures, these are the important points in zeolites. All the uses of zeolites are very important. To convert alcohols directly into petrol, we can use a zeolite called ZSM5. It is the name of the zeolite called ZSM5 as a catalyst in zeolites are mainly used as a catalyst in petrochemical industries for cracking of hydrocarbons and isomerization. Next continuation. Let us see some examples. Which of the following is cross-link formation in silicons? Cross-link formation, straight chain cross-link. So answer is C. This is called cross-link formation of silicons. So what are cross-link formation of silicons? I'll just write it here. Please make a note. So the cross-link formation of silicons is nothing but in which the silicon atom is linked with three oxygen atom, one methyl group. Silicon atoms are linked with three oxygen atoms and one methyl group. It is called as one methyl group, three oxygen atoms. It is called cross-link formation silicon. Next, compounds used on thermal insulators is it is asbestos. Compound used on thermal insulator is asbestos. So next, more about silicons and silanes we are going to discuss with advanced level. So now I'm sharing that to you. So please make a note of it. So now share screen here. Here I'm doing now. Next concept in the same session. So these are also very, very vital, important uses. So let us start now. Yes. Continuation of P block elements. That is silicons. Now, what is silicon? Silicon is found in two allotropic forms, that is amorphous form and crystalline form. Amorphous silicon is brown colored powder. Crystalline silicon is gray colored solid. Specific gravity of crystalline silicon is about 2.5. Its melting point is 1420 degrees C and boiling point is 2600 degrees C. Silicon is a poor conductor of electricity. It is insoluble in water but dissolves in hot alkali solutions. So this is nothing but the additional material for IIT advanced level. So please listen carefully. All these PPTs you make a note in your classwork, then only it will be easy. Now coming to silicates, these are the compounds of silicon with strong SiO bonds. In these compounds, silicon is coordinated tetrahedrally by four oxygen atoms to give SiO4 units. The SiO4 units may exist as discrete tetrahedral or may combine with each other by sharing oxygen atoms to give chains, rings, or sheets. As I told you, it can be formed as one unit or it can share by oxygen atom with each other and combines to form chain structures, ring structures, or sheet structures. They are abundantly distributed in nature in the form of silicate minerals and aluminosilicate clays. Most of silicates are insoluble in water. So this gives additional information based on silicates. Now we have structure of silicate. We have silicates, types of silicates. As I told you, types of silicates we didn't discuss. Now we are going to discuss orthosilicate. First is what? Orthosilicate. Each and every type of silicate they'll ask in the examination in the objective based on structure-based question they'll ask in the entrance exam. The formation of SiO4 4- unit involves sp3 hybridization of silicon atom and it has tetrahedral structure. Silicon atom lies at the center and the four oxygen atoms lie at the four corners of the regular tetrahedron as shown below. You can see the structure here easily. So this is called silicon tetrafluoride, tetraoxide with oxygen atoms is white color and black color is silicon atoms. So this is called tetrahedral unit, and it undergoes what type of hybridization? sp3 hybridization, and these are called as orthosilicates. What these are called as? Orthosilicates. Orthosilicates. So for example, in phenacate, and these orthosilicates are useful in replacing the cation exchange. Cation exchanges, it can exchange with cations such as magnesium, iron, manganese. Magnesium, iron, manganese. So it will form orthosilicate. So like the compound it forms is ZnSiO4, zinc. Zinc orthosilicate, ZnSiO4. Next we have iron SiO4, manganese SiO4, and magnesium SiO4. So some other cations with preferred coordination number of 6, in which SO4 4 minus ions are so arranged to provide. So in place of the cations, it can exchange with these compounds. So these are nothing but what? Orthosilicates. These are called what? Orthosilicates. Next continuation. Next we have pyosilicates. These involve discrete SiO4 2 minus 4 minus ions units in which, so these are nothing but it contains Si2O7 6 minus ions. It contains what? Si2O7 6 minus ions, in which each silicon is shared with 4 oxygen atoms and each oxygen is shared with 2 silicon atoms. So in which the SiO4 tetrahedral share one oxygen atom. SiO4 tetrahedral share one oxygen atom. It shares one oxygen atom, and of this type, simplest ion of this type is, the simplest ion of this type is Si2O7 6 minus. The simplest ion of this type is Si2O7 6 minus ions. In this ion, two SiO4 tetrahedrals are joined via one oxygen atom. So these tetrahedral units are joined by means of one oxygen atom. Disilicates containing a discrete Si2O2 units are very rare. Example is mineral thortevite. This formula they ask, that is scandium. Scandium pyosilicate. Scandium pyosilicate. The formula is Sc2Si2O7. Thortvetite. It is called what? It is, the name of this compound is thortvetite. Thortvetite, and even with lanthanide also it can form Ln2Si2O7. So lanthanum pyosilicate, lanthanum pyosilicate. The SiO-Si angle varies from 131 to 180 degrees. The SiO-Si angle is 131 degrees to 180 degrees. It can be anything. So linear, like. So these are called pyosilicates. These are called what? Pyosilicate. It contain one Si2O7 6 minus ion. In this ion, two SiO4 tetrahedral units are joined via oxygen atom. Very, very important. Please make a note. Next continuation. Cyclic silicate. It is found when three or more. Cyclic silicate is found when three or more SiO4 4 minus units condensed by sharing two oxygen atoms per tetraatom. They are sharing two oxygen atoms. Thus, three SiO4 4 minus units condensed to form Si3O9 6 minus ions. Very, very important. This structure-based question they'll ask. See here, each tetrahedron. So when three or more SiO4 units, 1, 2, 3, three or more SiO4 units condensed by sharing two oxygen atoms. These are sharing by two oxygen atoms per tetrahedron. Thus, there are four SiO4. Thus three SiO4 4 minus units will condense to form. This is called Si3O9 minus. Si3O9 minus ion. So this is called cyclic silicate. This is called what? Cyclic silicate, in which three or more SiO4 4 minus units condense by sharing two oxygen atoms per tetrahedron. They condense by sharing two oxygen atoms per tetrahedron. This point is important. They will definitely ask in the examination. Next continuation. Structure of silicates, cyclic silicates. Similarly, 6 SiO4 4 minus units condense to form. First we have done 3, next we have 3 to form Sa6O18 12 minus ion. The anion occurs in wollastonite, that is Ca3SaO3 Sa3O9, and benitoite BaTi Sa3O9. And the anion present is in this compound. What is the anion present? It is nothing but Sa6O18 12 minus, and this is called beryl. Beryl is a mineral which contains aluminum, beryllium, silicon, and oxygen. So it is a mineral, and it is in this the anion is Si6O1812 minus. They'll ask this mineral formula or they ask the anions. So benitoite and wollastonite. Wollastonite formula is what? Calcium, that is Ca3Si3O9. It is called wollastonite. And what is benitoite? It is BaTiSi3O9. BaTi. This is Ti is nothing but titanium. Ba is called barium. Barium, titanium, Si3O9. And here this is the anion in this is present, that is mineral beryl. It is nothing but Si6O18 12 minus. The charge you have to remember 12 minus. If you don't remember the charge, 3 aluminums and 3 berylliums. So aluminum is 6 and this 3 is 6 again. So 6 plus 6, 12. So automatically this becomes 12 minus. Because 2 aluminums means 2Al plus 3, it is equal to 6. And 3 berylliums means 3 Be plus 2, it is equal to again 6. So 6 plus 6, 12. So 12 positive, definitely this should be negative to become a neutral compound. So like this, if you can understand, it will be better. So these are called cyclic silicates. These are called what? Cyclic silicates. The general structure is SiO3 taken n times 2n minus. The general formula of this is SiO3 taken n times whole to the power of 2n minus. You can say this easily, you can understand. So for example, if I take n is equal to 4, so n is equal to 3 or 6. N is equal to 3 if I take Si3, 3 3s are 9, Si3O9, 2n minus. What is the charge of it? That is 3 2 to the 2 is a 6 6 minus. Like that you will get. So SA6O8 12 minus. So if n is equal to 6, n is equal to 6, it becomes SA6O18 12 minus. So the general formula of cyclic silicate is SiO3 taken n times 2n minus. The general formula of cyclic silicate is SiO3 taken n times 2n minus. In cyclic silicates, we have infinite chain silicates also. And for this continuation now, so please note down the general formula, is very important. So this is called SiO6, Si6O18 12 minus. This is called cyclic silicate. 1, 2, 3, 4, 5, 6 tetrahedral units. How many? How many silicons? That many tetrahedral units. So 6 silicons are there. So it has 6 tetrahedral units. How many tetrahedral units? 6 tetrahedral units are joined together by sharing 2 oxygen atoms with each one. Joined together, 6 tetrahedral units. 1, 2, 3, 4, 5, 6 by joining with 2 oxygen atoms, by sharing with 2 oxygen atoms. Very, very important. These are called cyclic silicates. These are called what? Cyclic silicates. Next continuation. Chain silicates. Next we have the sharing of 2 oxygen atoms by each tetrahedron may also result in the formation of long chains. This gives rise to 2 types of structures, single chain and double chain. So what are single chain and what are double chain? We are going to discuss now. So what are single chain and double chain? Single chain, each SiO4 tetrahedron, these points are important. Each SiO4 tetrahedron shares 2 oxygen atoms to give single chains of infinite lengths and which have the general formula SiO3 taken n times 2 minus 2n minus. These are called pioxens. These are called what? Pioxens. What are pioxens? These are called single chain silicates. Single chain silicates consisting of the general formula SiO3 taken n times 2n minus. These are nothing but also cyclic silicates. Enstapatite, diopside, and spodumene. These are the different types of silicates. And enstapatite is nothing but magnesium silicon trioxygen, diopside, calcium magnesium silicon dioxide 2 times, spodumene, lithium aluminum silicon trioxide 2 times. So silicon trioxide 2 times, silicon trioxide 1 time. So these are called examples of single chain structure of silicates. Single chain structure of silicates. These are also called as infinite pioxenes. Pioxenes means metallic silicates. Metal silicates. What are pioxenes means? These are nothing but metal silicates. Metal silicate means definitely one metal is present. So example here magnesium, here calcium and magnesium, and here lithium and aluminium. So it may present one or two metals. So that's why these are called as metallic silicates. These are called as metasilicates. We can say metasilicates or metal silicates. We can say metasilicates. Next continuation. So these are joined like this, one up, one down, one up, one down, and so on. So SiO3 taken 2n minus. These are called pioxenes. and each tetrahedron possesses two unshared oxygen atoms. Each tetrahedron possesses two unshared oxygen atoms. You can see here two unshared oxygen atoms, two unshared oxygen atoms. Minus minus are shared oxygen atoms, but these two are unshared oxygen atoms. Two unshared oxygen atoms. The linear chain is stacked parallel to one another. So to provide sites of 6 or 8 coordination number for the cations, they can provide to 6 or 8 coordination number. 6 or 8 coordination number for cations of cations can be replaced by this. Next continuation. Double chain minerals amphiboles. These are called double chain silicates. They are also called as metatetrasilicates. These are also called as what? Metatetrasilicates or amphiboles. Metatetrasilicates. Tetra means 4 silicon atoms. Simple it is. It consists of metal along with and the general formula. There are several ways of forming double chains. So the chains to form rings of 6 tetrahedral, and there are several ways of forming double chains. Forming formula Si2O5 taking n times 2n minus. This is the general formula. So example Si4 O11 6n minus etc. Examples of amphiboles is tremolite, that is calcium, magnesium hydroxide, silicon, tetrasilicon, O11 taken twice. So this is very very important. That's why these are also called as metatetrasilicates. Tetra means 4 silicon and meta means metals will be there. The OH group is not a part of silicate framework. The asbestos minerals are related to amphiboles, but their structures are more complex. So the coming in this is asbestos. Example for this type of silicate is asbestos. All these type of silicates, definitely they'll ask in the examination. Next we have sheet silicates. These are formed by sharing 3 oxygen atoms per tetrahedron. How many oxygen atoms? 3 oxygen atoms per tetrahedron, which results in a finite two-dimensional sheet structure, that is Si2O5 taken n times 2n minus. Example, mica minerals, talc, kaolin, clay, silicates of aluminum. These are all called sheet silicates. These are called what? Sheet silicates. So all these sheet silicates are very important. Silicates, zeolites, etc. You have to remember how many oxygen atoms are shared. This is called sheet silicate. How many oxygens are shared? By sharing 3 oxygen atoms per tetrahedron. How many oxygens? 1, 2, 3 only. For each tetrahedron, only 3 oxygen atoms are shared. 1, 2, 3, 1, 2, 3, 1, 2, 3, like this. So this is a 3-dimensional structure of 2-dimensional structure of sheet silicate. Next, 3-dimensional silicates. If a tetrahedral linked by sharing all 4 oxygen atoms. Here in the previous case, 2-dimension only 3 oxygen atoms. Now, if tetrahedral silicon are linked by sharing all 4 oxygen atoms, a 3-dimensional structure is formed, which has the formula SiO2, that is silicon dioxide. Quartz has a 3-dimensional such network. Such silicates do not contain metal ions. Example, quartz, tridymite, and cristobalite. Cristobalite, these are all nothing but silicon dioxides. In this network, if some of the silicon Si4 plus are replaced by A plus 3 and other cations, then minerals such as feldspar, zeolites, ultramarines, etc. are formed. So in place of silicon, metals will be replaced. What are replaced? Metals with cations, that is Al plus 3 and other cations. Then these minerals are known as feldspar, zeolites, ultramarines, etc. So feldspar, zeolites, ultramarines, etc. What is the formula of feldspars? It is sodium aluminum Si3O8. Feldspar formula is sodium aluminum Si3O8. Sorry, it is sodium aluminum, only one sodium. Sodium aluminum Si3O8. Si3O8. And next we have geolites. Geolites already we know. We have done it already. Geolites are nothing but shape selective catalysts. They are used in hardening of soft water. Sorry, softening of hard water. Next, ultramarines, etc. Very, very important, all these 3-dimensional silicates. 3-dimensional silicates contain if 1/4 of silicon ions are replaced by aluminum ions. A 3D framework of AlSa3O8 minus units result. This is called as feldspar. Feldspar means sodium or potassium aluminum silicate. Sodium or potassium aluminum silicate. If half of silicon ions are replaced by aluminum ions, then it is named as zeolite. Zeolite is Na2Al2SaO3 O10 is formed. This is called zeolites. What are zeolites? If half of silicon ions are replaced by aluminum ions in a set O2 taken 0.5 units. Then it is called as geolites. These geolites are shape selective catalysts, and these are used in softening of hard water. Now questions based on this, very, very important. Not only this, some other topics also we have given entire people. The correct statements about anhydrous AlCl3 are in non-polar solvent exist as dimer. It fumes in moist air. It is formed when Al2O3 is heated with Cl2 plus Sl2. It acts as Lewis acid. So answer is A, B, C, D. All the four statements are correct because aluminum chloride acts as dimer. We already know. It fumes in moist air. It is formed when aluminum oxide is heated with SOCl2 and Cl2. This is also correct. And moreover, aluminum chloride is Lewis acid because it is electron acceptor. Electron acceptor. Since aluminum chloride is electron acceptor, so it is called as aluminum chloride is electron acceptor. It is nothing but all the it is acting as a Lewis acid. So all the four statements are correct because aluminum exists as non-polar dimer. It is Al2Cl6. AlCl3 does not exist. It exists as Al2Cl6. Next continuation. The correct statements regarding titanium. Thallium, sorry. This is thallium is more stable in plus one state. This is true because due to inert pair effect. This is due to inert pair effect. Thallium is more stable in plus one state due to inert pair effect. First, H3BO3 has layered structure because of hydrogen bonding. Yes, it is also correct. Next, BOC2H5 taken thrice, that is boron along with ethoxy, gives green red flame when they catch fire. And thallium plus and aluminum plus are oxidants. Oxidant means they are good oxidizing agents. So I think answer is A, B, C only because these are reductants. These are called what? Reducing agents because aluminum plus and thallium plus they are thallium plus the aqueous. So they are not oxidants, they are reductants. So answer is A, B, and C are the right options. So these statement-based questions are very, very important. All these questions you please make a note. Definitely you're going to get questions in this. Next, the elements that melt below 30 degrees C are sodium, cesium, potassium, gallium. You know it is gallium because it is liquid non-metal. Gallium is liquid at room temperature. It is liquid at room temperature, so it is nothing but 30 degrees C means above room temperature, so automatically it will melt. So answer is D, B and D. So B is nothing but cesium also. Another metal is cesium. So cesium and gallium will melt at temperature below 30 degrees C. Next continuation. Which of the following is formula of sodium metabolite? Sodium metabolite means NaBO2. Na2B4O7, this is borax. Sodium metabolite is NaBO2. Simple it is. It is nothing but NaBO2. From borax B test, you will be getting this. Borax B test. But here sodium metabolite will not give color. Next continuation. The most basic oxide among the following is. So for basic oxides, you need to see the oxygen states. Aluminum in plus state and this thallium in thallium oxide. This is Tl2O. It is nothing but thallium in plus 1. And this is indium in plus 3 state and gallium also in plus 3 state. So the most basic oxide is thallium oxide. So answer is D because thallium in its lower oxygen state is always basic. Next, a common constituents of gemstones, ruby, sapphire, and emerald is silicon dioxide, aluminum oxide, chromium oxide, Fe2O3. So answer is aluminum oxide. So this is a constant of gemstones, ruby, sapphire, and emerald. Next, aluminum is used as reductant in the extraction of metals because it is cheap, it has low ionization values. Delta H of aluminum iron oxide is high, it forms alloys readily. So answer is heat of formation of aluminum is very high, it is around 2000 degrees C. So that's why answer is C. Next question. The correct statement regarding B2H6 is the correct statement regarding B2H6. B2H6 has planar structure. Each bond forms covalent, four covalent bonds. Six atoms are in the same plane. No, four atoms are acidic in nature. So straight away you can write here structure of B2H6. If you see here, B hydrogen B and four terminal hydrogens. They are in the same plane. Not all the six hydrogen terminals. Four hydrogen terminals are in the same plane, and this lie above and below the plane. Above and below these two terminal hydrogens. These two are called terminal hydrogens. Terminal hydrogens lie above or below the plane. And B2H6's planar structure. Each boron forms four covalent bonds. So one boron forms one, two, three, four covalent bonds. So each boron forms four covalent bonds. It is right. Six atoms are in the same plane. No, it is wrong. Four atoms are acidic in nature. That is four hydrogen atoms are acidic in nature that they are telling. So answer is only six atoms are in the same plane. Incorrect statement. Six atoms are in the same plane. So answer is what? Option C. Next question. Ferric alum reacts with sodium hydroxide solution to form ferric alum. Alum means double salt. What is alum? Alum is nothing but alum is double salt. It is used for purification of water. Double salt. So ferric alum means it contains iron. So a white gelatin precipitate, a green precipitate, a reddish brown precipitate, and no precipitate but evaporates ammonia. So answer is reddish brown precipitate due to the formation. Aluminium ferric column reacts with sodium hydroxide and forms a reddish brown precipitate. So I'll write the equation. Ferric column, ferric alum, ferric column reaction with sodium hydroxide. So please make a note. All of you, it's very important. So it forms FeSO4 plus NaOH. It forms 2NaOH plus FeO4 gives us to FeOH taken twice, ferric hydroxide plus sodium sulfate. It is nothing but dirty green precipitate. Dirty green precipitate. Dirty green precipitate. So after dirty green precipitate, slowly it changes to change in color, which forms reddish brown precipitate. Reddish brown precipitate. Answer is C. Next question. Metabolic acid exists as trimer arranged in layers linked by van der Waals forces, O-links, hydrogen bonds, covalent bonds. Metabolic acid. So it is answer is C because it is nothing but H3BO3 due to hydrogen bonds. In H3BO3, we have hydrogen bonds. Hydrogen bonds are present. Next question. Benzene and bozole do not differ in reaction with water, dipole moment, reaction HCl, number of electrons. This question is very important. Benzene and bozole do not differ in reaction with water, dipole moment, reaction HCl, and number of electrons. They do not differ in number of electrons because bozole is nothing but inorganic benzene. B3N3H6 is nothing but what? It is B3N3H6, inorganic benzene, bozole. Number of electrons, they are similar, but reaction with water, they are different because it is not aromatic. It is not aromatic compound. Only the structure is similar. That's all. whereas benzene is aromatic. Benzene is what? It is aromatic. So aromatic compounds will have different reactions with water, dipole moment, etc. But bozole will have different. Bozole is called what? Inorganic benzene. Formula is B3N3H6. BF3 undergoes partial hydrolysis in water. That is, boron trifluoride undergoes partial hydrolysis in water to form H3BO3 only, H3BO3 plus HBF4, HBO2 taken there is only H3BO3 plus HF only. So it is nothing but H3BO3 plus HBF4. You can see the reaction. So it undergoes partial hydrolysis to form H3BO3, that is orthoboic acid, plus HBF4. HF reacts with B2O3 or borax in the presence of concentrated sulfuric acid to form HBF4, BF3, BF3HSO4, and SO3F. These questions we are given based on P block elements entirely. So we'll be getting like these questions more and more. So that's why should be thorough with all this. So hydrogen fluoride reacts with B2O3 or borax to form BF3. BF3 is electron deficient compound. BF3 is an electron deficient compound. It is also called as Lewis acid. Electron deficient compound. Electron deficient compound also called as Lewis acid. Nothing but they are called as Lewis acids. Next continuation. Boron 10 isotope is used in nuclear reactors because it reduces the velocity of neutrons. No, it has low absorption cross section for slow neutrons, high absorption cross section for slow neutrons. It is a light nuclide. So it has high absorption cross section for slow moving neutrons to slow down the neutrons. High absorption cross section for slow neutrons. Next, these are the use of boron. Next, we have question based on silicon. Aluminum chloride is a good conductor of electricity. Why? Because in the molten state, when dissolved in benzene, it is in solid state and it dissolved in water. So only in the molten state, no, it is when dissolved in water, it forms Al plus Cl minus ions. So it is good conductor of electricity only when dissolved in water. In molten state or in dissolved in benzene in the solid state, it is not a good conductor of electricity because it is covalent in nature. It is what? Covalent in nature due to its covalent character, slightly covalent character. So due to its covalent character, it is like this. So answer is D. Next question. So these are the important questions from this session. More questions based on silicon we'll do in the next session definitely. And with this, I'm ending this session. So please follow what we have discussed. Thank you all and concentrate more questions on silicon, silicates and types of silicons. Very, very important. Thank you all.